Welcome back, everyone, to the Algebraic Graph Theory seminar. This week we have Logan talking about a new graph polynomial from the chromatic symmetric function.
Thank you very much for having me. Thanks for coming. And this is work that arose from an undergraduate research project over the summer with William Chan. And there we go. So a brief review of the chromatic polynomial and related things, first of all. So an n-coloring for the purpose of this talk is going to be a map from the vertex set of a graph to the positive integers 1 through n, so that whenever we have an edge between two vertices, they are assigned different colors by this coloring. The chromatic polynomial then is the unique function from positive integers to non-negative integers, such that chi-g of n is defined as the number of proper n-colorings of g. It's not immediately obvious from the definition that such a function would need to be a polynomial in n, but it is, among other things. One way you can show that is from this classic deletion contraction relation of Birkhoff. So for any edge, if you take the chromatic polynomial of the graph G, and then you take any edge of the graph and you delete that edge, take its chromatic polynomial, and then you subtract it from where you contract the edge, which is when you take its two endpoints and identify it to a single one, and bring all the edges together, then you get this equality. And a brief explanation as to why this is true. We see here, up here is a graph, and here we're doing it in somewhat of reverse to do a bijective proof. We are writing it as chi-g delete e is equal to chi-g plus chi-g contract e. So this is it with this edge deleted here. And this is one example of a proper 3-coloring of this graph. When these two endpoints receive different colors, this coloring is also proper on this graph because we can add this edge and it does not violate that condition. And on the other hand, this does not reasonably correspond to a coloring over here because what color does this vertex get? And you can see here, by the way, on the right, when I contract the edge, I keep both edges that were between this vertex over here and either of the two endpoints on the left. For the chromatic polynomial, this doesn't matter much because it doesn't care if there's multiple edges between a pair of vertices, but sometimes it does for other things we consider. So my practice is to keep them in unless I really need to get rid of them. Now, what if these two endpoints of this edge get the same color? Then clearly that's not a proper coloring in the original graph with that edge in, but we can obviously associate to it this proper 3-coloring when we contract the edge by giving this vertex the same color as both endpoints. And so this bijectively shows how this operation works. And one classic identity for the chromatic polynomial was shown by Whitney, among other things, in 1932, when he showed that if you sum over all subsets of the edge set of a graph, you get a sum over a sign for the size of that subset, and you get this n to the number of connected components of the graph using only the edges in S. And I'll reiterate, I'm bringing all of this up because I'm going to be talking about specializing chromatic symmetric functions to various polynomials, and it'll be easy to see how that works and why by understanding a few identities of the chromatic polynomial. In this context, I also want to give a bit of a sketch of how one would prove this identity. If you apply deletion contraction to an edge of G, and then in each of the two resulting terms, you pick a different edge and delete and contract it, since in both of those that edge is missing, well, overall, you're going to get a sum of 2 to the number of edges terms. And each term could correspond to contracting all the edges of sums from some subset S and deleting the remaining ones. The term for an S coming from contracting the edges in S, well, it's going to have sign -1 to the number of edges because in deletion contraction, we contract when we subtract when we contract and not when we delete. And as for where the actual chromatic polynomial at the end comes from, after we've deleted and contracting every edge, there's no edges left. We're going to have an empty graph with some number of vertices. How many vertices? If we look at the components of the graph, they are all going to contract along this edge to this one single vertex at the end here, and that's going to be true for each component separately. So it's going to have that number of vertices and no edges, and it's easy to check that the chromatic polynomial of such a graph is just n to the number of those components. One other interesting result on the chromatic polynomial is that it has interpretations when you evaluate it at negative integers. Perhaps most notably and simply, if you evaluate it at -1, you get the number of acyclic orientations of G, where an orientation means you assign to each edge a direction, going from one vertex to the other. And acyclic means that you cannot start from any vertex and travel along edges to return to that same vertex, only traveling in the direction of the orientation. And this proof is somewhat similar to the previous one in that you could do it by applying deletion contraction cleverly. And the simplest way is induction. You can check this is true for graphs with no edges, where you only have the empty orientation, and the chromatic polynomial is clear. And then you can induct using deletion contraction. Now I'll briefly say you do break into cases. One, when there is some directed path between the endpoints of the edge other than the edge itself, because then when you contract it, you would get a cycle, and so it's invalid as an acyclic orientation there. And otherwise, you'll be able to count it in both cases. Now, having summarized some properties of the chromatic polynomial, I'm going to bring in the chromatic symmetric function. Now, by the way, one thing I didn't say at the beginning, feel free to ask if you have any questions. You can either ask in the chat or you can unmute and say things. Maybe I'll take a moment here to briefly ask, are there any questions about what I've said so far? Okay. So the first thing you might ask when I say chromatic symmetric function is, what is symmetric about it? I'm going to get to that in a second. So first of all, this function is not a polynomial. It is going to be a function. We'll use x because x is kind of the bigger version of chi. At least that's, I think, the rationale. And it's going to actually be uncountably many variables, x1, x2, up through 1x for every positive integer. We're still going to be summing over all proper colorings, but instead of counting each proper coloring once and sorting it by how many colors it uses, we're going to give it this monomial, the product over all of the vertices in the graph of x sub the color it gets. Now to think about what this means for just a second, suppose I have a monomial here, x1 squared, x2, x3 for a 4-vertex graph. What is this telling us? Well, it's telling us that we've used 3 distinct colors because we have 3 distinct variables, but it's telling us a little more than that. It's telling us that the color 1 is used twice, and that the color 2 is used once, and that the color 3 is used once. So this is the added generality of the chromatic symmetric function. It tells you how many colors are used by a coloring, as well as how many times each color is used. So this function formally is a power series in these countably many variables over whatever coefficient ring we want to work over, as long as it's a field of characteristic 0. I'll use R here. And why symmetric? Well, it's symmetric because for a chromatic symmetric function defined in this way, if you take a proper coloring and you permute it, it's still a proper coloring. And so whenever you get that term, x1 squared, x2, x3, well, I could have just as well permuted those colorings, and I would have also gotten some term of the form x2 squared, x1, x3. And I could have also permuted the colorings across all natural numbers and gotten a different term, x4, x7, x11. I'm going to get one copy of each of these terms if I have one copy of the original term. So symmetric means that it is unchanged when I permute these indices of the variables. And to make it clear that this is indeed a proper generalization of the chromatic polynomial in the sense that you can actually recover it, if you set the first n variables equal to 1 and the others to 0, then you just recover the chromatic polynomial because, well, you're going to be counting each of these colorings once if they only use colors from that set and 0 otherwise. And to summarize what I've been saying here, computing x delta, where delta here is this graph that represents airline routes for a certain airline. And I don't know if this is out of date because I've been using this graph as a running example for a little while, but it might or might not be. But in any case, in this graph, here are 2 different proper 3 colorings. And notice that they give rise to different terms in terms of different types. From this first coloring, we get an x1 cubed, x2, x3, 3 blue, and 1 green and 1 red. Over here, we're getting a different exponent pattern, x1 squared, x2 squared, x3, because we're using 2 of one color, 2 of another, and 1. So again, just illustrating this added generality in that x of delta distinguishes these two proper 3 colorings, where they would not be distinguished by the chromatic polynomial. Deletion contraction. I talked about this at some length for the chromatic polynomial. It doesn't work nicely in the obvious way for the chromatic symmetric function. Why is that? Because each term has a total sum of degrees equal to the number of vertices. But in the traditional graph functions, if we contract, we have a smaller number of vertices. It's a function of lower degree. It can't really be equal unless we're doing something fancy to make them equal. So what Sophie and I did to address this problem is we consider a vertex-weighted graph. We have a graph, but it may also consist of a weight on each vertex that is a positive integer. Upon doing this, we can extend the chromatic symmetric function in the obvious way by allowing for each vertex, when we take its color, we also take that exponent, the weight of the vertex. So now we're not counting the number of vertices of each color, but the total weight of all vertices with a given color. But if we do that, then we can recover a deletion contraction relation. It's exactly the same as for the chromatic polynomial, with the addendum that when we contract an edge, we take as the weight of the new vertex the sum of the weights of the endpoints. And indeed, this is going to have the same basic proof as before. If we have a coloring, these numbers are vertex weights and the colors represent the colors. And if we look over here where these have 2 endpoints of distinct colors, then coming over here to the left, these are going to again form a proper coloring. And if we have them of the same color, then to fix the issue of the total degree, what happens is we take this green color that has a weight 3 and a weight 2, so this is forming, say, x3 to the 5th, and we add the weights so that we still are getting this x3 to the 5th term in the contracted graph. This is how we're fixing that degree issue and making this work nicely. Now, the premise of where this talk is going in terms of deriving polynomials from the chromatic symmetric function is going to be coming from expressing it in different bases and deriving different information from this and transforming those bases into polynomials. Let me take a brief moment here to ask if anyone has questions about the chromatic symmetric function. Okay. So what do I mean by expressing things in different bases? To use the chromatic polynomial itself as an example, note that chi g is a polynomial. It's counting colorings of g by the number n of colors used. And we're using each of these to give some sort of term. Polynomials have bases indexed by non-negative integers. And it is true that different bases of a polynomial space can yield different information. For example, in the traditional basis, where you're just using x to the k for each k, this is giving this representation where those Cn, the coefficients of the chromatic polynomial, determining specific ones you can do in special cases. In general, it's hard. In general, you can express it in terms of signed sum of certain kinds of subgraphs appearing in the graph, but it's kind of gross. But the overall sequence of the Cn is known to have many nice properties. It alternates in sign. The absolute values of the coefficients form a log concave sequence. There are lots of nice things that can be said about these. On the other hand, let's take a different basis of the polynomial space. For example, if we define this following factorial where x sub n is this product, x times x minus 1, etc. downwards. If we were to write the chromatic polynomial in this basis with coefficients d sub n, then the d sub n has a specific combinatorial meaning. It counts the number of partitions of the vertex set into n non-empty independent sets. So this is giving a simple example to explain how different bases are giving us different combinatorial information and allow us to see it more easily when it's all coming from, in fact, the same function. The same is going to be true with the chromatic symmetric function, except that we need to figure out what the basis is here. For it counts not only how many colors are used, but how many of each color is used. So these bases will be indexed by sets of positive integers. And when a set adds up to n, it is called an integer partition of n. I should be more specific here. It's a multi-set of positive integers in general. And we will write this as an ordered tuple where we require that the numbers in the tuple are weakly decreasing so that it's uniquely represented. So for example, the set that contains 4, 2, and 2 copies of 1 is an integer partition of 8, and we would use this notation to represent it. And a basis of the chromatic symmetric function is going to consist of objects that are indexed by these integer partitions. So here's an example of one. Let us suppose we're looking at the chromatic symmetric function of a single vertex of weight n, which is what this notation here means. If I'm looking at a vertex of weight n, then I can color it 1. And if I color it 1, that's going to give me this x1 to the n term. If I color it 2, I get an x2 to the n, and so on. And this is a symmetric function that we define to be the power sum symmetric function. P sub n is the sum of the nth powers of all the variables. We can further define that p sub lambda, where lambda is a multi-set of integers, to multiply across the distinct integers. So if we have this graph whose vertex weights are equal to the parts of that thing, then we're going to get that sum, and it's going to multiply across disjoint unions. It is easy to see that the chromatic symmetric function multiplies across disjoint unions. So the chromatic symmetric function would be this product of power sum functions. And if you wanted to get an expansion in terms of monomials, you would multiply all of these out. Let me briefly clear the screen for the next part of the slide. So if we're looking at this basis of symmetric functions, what does this say if we look at chromatic symmetric functions and try to do this? If we do this for a vertex weighted graph, Stanley proved this theorem for unweighted graphs, and Sophie and I slightly generalized this to vertex weighted graphs. You might see that this formula looks familiar. We have a sum over all subsets of the edge set. We have a -1 to the number of edges, but instead of an n to the number of connected components, we are now getting a p sub the integer partition whose parts are the weights of the connected components. So we're distinguishing these connected components now by their total weight. And how could we prove this? It's going to be the same proof method. We're going to delete and contract using the vertex weighted version of deletion contraction. And we're going to get this sum corresponding to contracting the edges in the subset S. We are going to have that same sign. But now when we have reduced it to having no edges left, each component that had weight m in this with these edges is going to contract to a single vertex with that weight m. So in the end of all of this, we are going to have those number of vertices equal to the number of connected components, but now we have this extra information about their weights. And as we've said above, this has this chromatic symmetric function that gives us this product of power sum functions. So this is how we're getting a basis from multi-sets of positive integers, and how we can interpret those coefficients. In this case, the coefficients of the p lambdas tell us something about the sizes of connected partitions induced by subsets of the edge set. And note that if we wanted to pass in this context the chromatic polynomial from xg, we could set each p sub k to be n. And in effect, this also would turn p lambda into n to the length of lambda, the number of parts. And as we saw before, this actually just takes us to the chromatic polynomial as well. This is equivalent to setting the first n vertices in variables to 1 and the rest to 0. I also mentioned before the evaluation on negative integers. This is somehow captured by a different basis, this elementary symmetric function basis. So in this context, E sub n is going to be the sum over all monomials within distinct variables. This is what you would get if you took the chromatic symmetric function of a clique. And we have to adjust by a factor of 1 over n factorial because, for example, the coloring 1, 2, 3 on this triangle occurs 3 factorial times. And we can again define E lambda to be the product of E's, and that would represent the chromatic symmetric function of a disjoint union of cliques. Again, up to this constant. So what Stanley showed is that if we take an unweighted graph G, and we take a polynomial by mapping the E lambdas to n to the length of lambda, or equivalently each ek to n, then the coefficient of the n to the k term there is the number of acyclic orientations of G with k sinks, which are vertices that have no outgoing edges. So the chromatic symmetric function actually refines this property of the chromatic polynomial. We can now enumerate not only acyclic orientations, but we can enumerate them by number of sinks. And by this property of passing to a different polynomial by mapping all together each E lambda of the same length. I will also add briefly, there is a version of this theorem for weighted graphs that Sophie and I discovered, but it is more complicated than really needs to be discussed here. But it uses deletion contraction, which is fun. Does anyone have any questions about this so far? Here, the main point I'm getting across is this is how I'm going to be forming polynomials from the chromatic symmetric function is I'm choosing a basis and I am mapping the basis element that uses a total of k distinct integers to the polynomial n to the k. And how do we do this? How are we going to make bases? That we're going to be using a theorem by Cho and van Willigenburg, as well as I will briefly expand this because I'm going to be using this name a few times, but it was too long to fit in the slides. This is Farid Al-Nayafard, Victor Wong, and Steph van Willigenburg in a recent paper from this year. And I will be notating this triplet of names as AWVW so that it fits in the theorem heading. And so Cho and van Willigenburg showed this theorem for unweighted graphs, and then it was generalized to weighted graphs by Al-Nayafard, Wong, and van Willigenburg. If we have a family of connected graphs where the ith graph has a total weight of I, then these chromatic symmetric functions formed by those graphs are algebraically independent, meaning that we can form a symmetric function basis from them by taking the disjoint unions of these graphs and defining this x sub lambda is going to be the disjoint union from chromatic symmetric functions, and these xg lambda are going to form a basis. This leads to some interesting questions, naturally. These bases I mentioned earlier, the power sum and the elementary symmetric functions, these bases were already known as kind of classical symmetric function bases. But it also turns out that they can be represented by chromatic symmetric functions of possibly vertex weighted graphs. So it seems natural to wonder if other families of vertex weighted graphs are going to give rise to interesting symmetric function bases. So this is kind of where we were going with the initial goal of this project, was we were going to be looking at using trees for this. So as we mentioned, if we have a symmetric function f, we can in principle define a polynomial from it, which we could call chi f of x. And I'm switching to hex here, so this is easier to see because I'm going to be using n for like numbers of vertices and things. And chi f of x is going to be the polynomial resulting from letting each power sum function go to x. And as we discussed, if GW is a vertex weighted graph, if we apply chi to the symmetric function xGW, we recover chi g. Note that we lose the weights. We do lose the vertex weights if we apply this to a weighted graph, because in the end, all we care about is when we pass to the polynomial is the number of connected components. We lose the information about their total weights. But in any case, this is how we get this. So suppose we want to look at an expansion of the chromatic symmetric function into some family of trees. Let's say it's a family of trees such that T sub I has I vertices. Suppose that we have its expansion here. Let's apply this map chi to both sides. On the left, we're going to get chi g. On the right here, we're going to get chi t lambda. Well, t lambda is, remember, it's a disjoint union of trees. And to highlight here, t lambda is equal to some disjoint union of trees. And what's the chromatic polynomial of a disjoint union of trees? Each one is going to give us an x times an x minus 1 to a bunch of powers. And if we have the length of lambda of them, then we are going to get x to the length of lambda, and then we're going to get x minus 1 to the remainder. Now here's the critical fact though. This value that we get does not depend on t. It does not depend on the tree, right? Because every tree has the same chromatic polynomial. It only depends on how many of the trees there are, how big the forest is. So this sum of coefficients, if we were to sum these a lambdas over all of the partitions that have a given length, that sum must be independent of the choice of the ti. So in particular, if we take the polynomial arising from expanding in this tree basis and setting the xti to x, that sum of coefficients will be independent of the choice of tree. So we can well-definedly call this the tree polynomial of a vertex-weighted graph and denote it by tau. And one might notice that something I did here is I talked to you about being able to use graphs of any, where G sub I has weight I, but here I've required that the tree I has I vertices. Why do I do that? Well, it's precisely because we need these to come out equal. If I have some of my trees, if some of my trees have fewer vertices than their total weight, then this is no longer in general going to be true and work out nicely, of course. You could, of course, try to do something similar by using a family of weighted trees, but for this particular result, we're going to just assume that they each have I vertices. Now, how are we going to learn more about this tree polynomial? We'll go back to the result from Alefeanard, Wong, and Van Wittigenberg, and that paper had another fact. If we let P sub n be the path of n vertices, then if we have a function that maps the power sum function Pn to the chromatic symmetric function xPn, that map is an involution. It also maps xPn to lowercase pn. This is a fantastic fact that tells us some very interesting things and is part of why this project was started, to figure out what's special about paths, and also stars have this property as well, although I'm not going to be needing that in this talk. They also showed that those are the only two families of graphs that have this property. And why is that? It ultimately comes down to the fact that paths and stars are the only families that if you take edge subgraphs of them, they remain in the family. Subgraphs of paths are still paths, subgraphs of stars are still disjoint unions of stars. There's no other graph family that has that property. So we can discover some sort of reciprocity relation. As you might be horrifyingly seeing, I have included a long series of calculations here, but I'm going to go through them. So let's suppose that we have our chromatic symmetric function xg. We're going to say a lambda is the coefficient of p lambda. And we want to calculate, well, we want to figure out, can we figure out the coefficient of the tree polynomial from this? Well, this coefficient by definition is what happens if we take xg and we sum the coefficient of xp delta, as delta is ranging over all partitions of that length. If we expand xg, then we're going to have this sum on the right here. We're expanding into p lambda, and now it suffices to understand how the coefficient of the path delta in p lambda. As we said before, these functions have an involutive relationship. That coefficient is the same as if we look at the coefficient of p delta in xp lambda. Now that we're doing that, well, let's remember, p lambda is a disjoint union of length of lambda paths. And we have our nice result on the p lambdas that we have this function that xg is the sum over all subsets of the edge set of this -1 to the cardinality of s p lambda of s. And when you have a disjoint union of paths, you can very quickly figure out what is happening with that. You end up getting, basically, if you have n total vertices and you have k parts in your set of paths, then then I can pick some of the edges. Oops, that's on the wrong. Okay. I can pick some of the edges to bring it to the correct thing. I can sum only from m equals 1 to k, because for me to be getting a p delta out of xp lambda, it needs to not end up with too many parts. Length of the number of paths has to be less than the number of components I want to end up with. And how many ways can I get something out of this? It's going to be the n minus m edges. I can choose k minus m of them. This part I would need to draw out because this is the part I always confuse myself with exactly how this number comes about. But basically the point is that you have paths with here the path has length m. There's m, meaning that there's m distinct ones of them. And I want to end up with more components. I want to end up with a total of k components. And so I need to choose k minus m edges to turn these m paths into k components. And this is the number of ways I can do this. And I'll end up with this sign. And from here, it's just going to be some algebraic simplification. I can pass the n minus mk, choose m inwards. I can factor some things out. And over here on the right, well, this number, the sum over all partitions of length m of a lambda is, as we saw earlier, this is in fact just the x to the m coefficient of chi g. And so what this is saying, if you'll see from the beginning, is that we can express the x to the k coefficient of tau g as some reasonably natural sum of the coefficients of chi g. So these polynomials are intimately related. To start with that, does anyone have any questions? So let's compare these two polynomials. I'm not going through the details of how these are derived, but essentially pretty much everything here can be derived from some sort of using of the previous relationship on coefficients and some algebra. As we said before, if you take chi GW and make that definition, you could define chi GW to be chi XGW. You lose all the information about the vertex weights. Tau GW does something different. You can evaluate that from tau GW, you can recover tau G, which is the function on the unweighted version, by dividing by what ends up being a factor of x minus 1 to the excess weight of the graph. So every vertex has weight at least 1. So in some sense, this number, weight of G minus number of vertices, is this excess weight number. So the tree polynomial retains that value. On the other hand, we can, of course, from the chromatic polynomial, recover the number of vertices. However, for a tree, you might have noticed tau of any tree is x, because there's at least one basis in which we can express tau t, which we can express it in any basis in which that t is one of the choices of graph. So tau doesn't tell you the number of vertices. Chi tells you the number of vertices, but doesn't tell you anything about the weight. Tau tells you something about the weight, but nothing about the number of vertices. So there's some kind of dual information encoded in that sense between these two functions. They do both have a deletion contraction relation, and chi has this simple one. The tau one is only true for unweighted graphs, even though in principle, of course, it does have meaning on weighted graphs. But you get a tau g delete e minus, this is an x minus 1 times tau g contract e, which makes some sense. Remember, we need this extra x here to account for the fact that tau doesn't remember how many vertices we have. One thing that does carry over actually exactly is clique joins. It is well known that if you have a graph that is formed by two graphs, G1 and G2, intersecting in a common shared clique, then you can express their chromatic polynomial by taking the product of these two graphs and dividing by that of the clique. It turns out that you can check by just basically factoring through that process from above that the same thing holds for tau, which is interesting. One other fun fact I'm going to share here is that we can also have a different relationship between tau and chi as some sort of evaluation fractionally. For example, so chi g we could recover by, we have to somehow incorporate the information about the weight of the graph, but we can recover it from tau gw of x divided by x minus 1. And there is likewise a reverse formula you could use to get to tau from chi that again uses an evaluation at x over x minus 1. This might be one of the more intriguing things that came out of this, and I don't know what exactly that means. I will show in a few slides that the tree polynomial does have a combinatorial interpretation for things in its own right, which suggests that the chromatic polynomial also does for certain fractional evaluations, which is interesting to me, and I'm curious if anyone here knows about that, because I tried to do some research and I did not find a whole lot on anything of this form. That would be something I would like to consider in the future. And so far what I've shown you is that tau has some interesting relationships with chi g. And sure, that's true. Is tau interesting in its own right, though? Why would we care about tau if it just comes from chi g? This is probably the question you've all been wondering. Well, let's start with, we know that chi g of n, we defined it originally, in fact, as the number of proper n-colorings of g. So what we found is we found some coefficient evaluations for tau g. Can we say more about those? Do those coefficients or its evaluations have some sort of meaning? To do this, we're going to go into a little bit of tut style activity stuff. If you have a graph G, we're going to give some arbitrary order to its edges. If we do this, we call a broken circuit of G to be its cycle, a cycle of it minus the smallest edge. And we say that the broken circuit complex of G consists of all of its edge subsets that contain no broken circuits. One thing that's worth noting, all of these elements are certainly at least forests, because if you contain a cycle, then you certainly contain a cycle minus its smallest edge. But in fact, you only contain forests that are not missing from a cycle its smallest edge. In this sense, we call elements of BG internal forests then, where this name is related to internal and external activity. And we will call the maximal elements of this thing internal spanning trees. Note that this does not need to actually be a spanning tree if the graph is disconnected. If it's connected, it is actually a tree, of course. But even if the graph is not connected, I'm still going to call maximal elements of this thing spanning trees, even though they technically have some extra components. One thing that Whitney showed in that same work where he demonstrated the previous result I'd mentioned about sums over edge sets is that in fact you don't have to sum over all of the edge sets. It actually suffices to only sum over those edge sets in the broken circuit complex and take the exact same formula, -1 to the number of edges, x to the number of connected components. Which is also nice when you remember that the number of edges in this case is actually just a function of the number of vertices and the number of connected components, because they're forests. So one thing that arises, and I'm not going to go through the algebraic details of deriving this, but one can show as kind of a midway point in the previous derivation I showed you, is that tau g of x could be expressed as this sum. Now, what is this value, this coefficient of t to the k and chi g of t? Well, as I said up there, with that formula, we could interpret that as elements of the broken circuit complex, up to some sign. And those are forests. Those are forests with k connected components. And what is this over here but the chromatic polynomial of a forest with k connected components and n vertices? So we notice that from this evaluation, we can actually immediately conclude that tau g of n is actually just the number of properly n-colored internal forests of G. This just arises immediately from this intermediate step. And we did have in further evaluations we were able to show of tau g of n, but this is perhaps the simplest and easiest one to state. So it still counts colorings of something, but not colorings of the whole graph, colorings of these internal forests. And one other thing I wanted to share a brief outline of is we can find a different interpretation of the coefficients that also arises from this. It is possible to show that the absolute value up to a predictable sign of the coefficient of tau g is equal to the number of ordered pairs of edges and trees, where the edge set is some edge set, it's ordered, and it has some number m of edges, and it splits g into k connected components, a k cut set, and t is some internal spanning tree of g, with this special property that if one of the edges from E is in it, then there is some smaller edge that's not in it, and such that EJ is in its fundamental cycle, where here fundamental cycle means the unique cycle formed by adding E sub I to T. Where does this basically come from? We can map the edge set to the tree minus the edge set, and what this means is we can work entirely within this broken circuit complex during our proof. And there's some slightly tedious algebra I'm not going to go through, but ultimately this question ends up being equivalent to taking a fixed element of the broken circuit complex with k components, and we want to sum over all other elements of this complex that are bigger than it. And it's going to be a weighted sum over its number of connected components. And how are we going to use this fact? We're going to inductively reduce this sum. What we want to do is basically we want to end up showing that this sum ends up only applying to these maximal things, basically. These T is an internal spanning tree. And we want to show that if we reduce the set of U to only those, that the sum remains unchanged. And if that remains unchanged, then this ends up showing this. And what's the argument there? We start with all of these U's, but we inductively reduce the sum to add this second property, namely that we're trying to build towards a spanning tree, but in particular, we care about the property starting here, that if U has these EI and EJ, then it satisfies that if it contains an EJ, then there's some EI outside of it that is in the fundamental cycle of something else. Basically, the short summary of this is that at each step, we're going to remove pairs of elements that have opposite signs. In particular, for each sigma, which is an element of this broken circuit complex, if we've already done this process for edges E1 up through EL, and EL plus 1 is not in sigma, and adding it would properly decrease the number of connected components, then we can remove sigma and sigma union that edge. Then the bulk of this proof consists of showing that A, both sigma and sigma union that edge are still in the set at this point, and B, that this actually removes all of the edges over time that would, all of the subsets of U over time that would be a problem. This is a very brief sketch, and I don't know how enlightening this is, but the point is that we can show cool things about this tree polynomial by passing to this broken circuit complex. There's somehow some fundamental relationship between these two. And it tells us that there is a combinatorial interpretation for the coefficients and the outputs of this polynomial, despite the fact that it comes from interesting sums and fractional evaluations of the chromatic polynomial. So that's part of what I'm trying to share here, is why I think this is interesting. And I feel like there's some more interesting things to be found here as to what exactly this is telling us and why. So to conclude, the work in this talk is based on that paper, a graph polynomial from chromatic symmetric functions by myself and William Chen. It is on the archive. And that is my talk. Thank you for coming.
Thank you very much. Are there any questions for Logan?
I have a question. Excuse me. You apply. Is it possible to find to create polynomial to obtain chromatic number of classes of graph, for example, other classes using polynomial? In this type, we have watching polynomials from a chromatic number. Is it possible to do reversely? I have a graph, the classes of graph, a general. Is it possible to obtain general polynomial which can compute the chromatic number? I think it's about vertex coloring, vertex weighted. Is it possible to work on edge weighted and getting? Is it possible to study, or is it understandable to do that?
You're asking about edge-weighted and coloring edge-weighted graphs?
Yeah, edge-weighted.
Not specifically in this context, I haven't, although I have worked with the chromatic symmetric function, and there is a generalization of this to an object called the V polynomial. I'll type it into chat real quick. There's a lot of papers on the subject by Joe Ellis Monaghan and others. Let's see. The V polynomial, this is a generalization of the chromatic symmetric function that does include edge weights, and it also allows the vertex weights to come from an arbitrary semigroup. I'm not sure if that's the right word. Something where if you add two elements, that stays in the group, and that's kind of the only thing you need. The short answer is that I haven't tried that yet, but it's possible you could try that. I have established some results on the chromatic symmetric function by reducing from this V polynomial to that, and that covers edge weights. So it's possible there's a way to bring that a step further down and try to say something about this with regard to these chromatic and tree polynomials. I'm not entirely sure yet, but that would be my guess, is that would be the way to go.
Thanks. I have a first question about, is it possible to construct a polynomial to compute chromatic number of graph?
I don't think I understand what your question is, perhaps.
For example, chromatic number of, for example, path is 2, but I don't know. The last question, excuse me, sorry. Are there further directions to study in this concept, in this talk, to have some result, sensible result? Open question, open problems in this topic.
I mean, I think the short answer, so if I'm understanding the first part of your question correctly, I have not yet studied which families of graphs have a fixed tree polynomial output number. I'm not sure exactly what your question was with regards to the chromatic polynomial. As far as research directions goes, mostly as far as I know, this polynomial is original and just created, but just up from this survey we did over the summer project, it seems to have startlingly interesting connections to the chromatic polynomial. I find it interesting that it's dual in that it preserves the notion of excess weight, but loses number of vertices. And I find it interesting that it arises from certain fractional evaluations. One thing I would hope for example, that's explicit, is that there could be applications from this to the conjecture that the chromatic symmetric function distinguishes trees. This is unknown. It would be surprising, right, when you think about it, because the chromatic polynomial completely does not distinguish trees in any way. But it's still unknown if the chromatic symmetric function does. It's possible this simpler to understand tree polynomial maybe could say something about that if you try to examine it using different bases of trees. I also just think it's interesting to figure out what's up with this fractional evaluation. I really want to know if anyone knows about that.
Thanks.
And I see here Victor mentioned something in the chat. I see, those are the only unweighted families that are closed under subgraphs, but it might be true that they are the only such families. Okay, thank you. Yes, that's my inaccuracy.
I have a question. Maybe this was just a misunderstanding on my part, but it seemed like you were saying that which set of trees you picked to construct your basis didn't affect the polynomial. Is that correct?
It does not affect the polynomial, no, which means that the sum of coefficients of fixed length is independent of the choice of trees.
Uh-huh. And so is that, I mean, in terms of like whether you stop with this polynomial or whether there should be some bigger polynomial above it, like do you feel like this is this evidence that there's that this is a specialization of something bigger, or is that just an artifact of sort of what's going on with the broken circuit complex?
I'm not entirely sure if I understand what your question is yet.
I guess my question is just like morally, do you like is the fact that this what how do you feel about the fact that that it doesn't matter which trees you're picking?
I'm not entirely sure yet. I think this general concept is interesting of turning these symmetric functions into polynomials for one thing. The fact that the chromatic polynomial and the acyclic orientation result of Stanley arises from this, if you were to consider it as an acyclic orientation polynomial enumeration. There's perhaps some sense in which it's not surprising that it should be independent of the trees, but I don't, the short answer is I don't know yet. This is still a pretty recent result, and I don't entirely know how I feel about it yet in terms of how interesting and likely it is to go to other things. I agree. I mean, obviously there's some extent to which one can argue it's an artifact of the fact that the chromatic polynomial agrees on all trees of the given number of vertices. But on the other hand, the fact that that fact is so relevant to the chromatic symmetric function and something related to it is not immediately obvious, given this whole tree isomorphism conjecture thing. There's some sense in which trees are kind of the simplest interesting thing. There are ways to express chromatic and their generalized symmetric functions as certain sums over weighted spanning trees and active trees that you get from them. So there is some sense in which if you understand trees in principle, you kind of understand these functions on all graphs. There's something fundamental about these functions on trees that I think is yet to be revealed. And it's possible that this is a step in the direction to understanding how exactly we're getting something from trees from this combination. I don't know.